Have you ever wondered what the cutting edge of AI has in common with that 3-pound computer sitting between your ears? Well, today we are diving into exactly that. We're talking about neural networks, this incredible bridge that connects biology to silicon, and believe me, it is changing everything. Let's get into it.
And no, this isn't some far-off sci-fi question. The link between your brain and the AI that's making headlines every single day is actually surprisingly direct. And understanding that connection, well, that's the key to unlocking this entire field.
So to answer that big question, we have to start with a term you've almost certainly heard buzzing around: deep learning. It's a huge piece of the puzzle, a massive reason for the current AI boom. But what does it actually mean?
Okay, so this definition gives us two really crucial clues. First, you've got this idea of layers. Just imagine a whole series of filters, where each one understands the world a little bit more deeply than the last. And second, maybe the most important phrase of all: inspired by the brain. That right there, that's where our whole story really begins.
You know, that inspiration from biology, it isn't just some vague poetic idea. It is absolutely fundamental to how these systems are designed from the ground up. And to see how, we need to zoom way, way in, down to the single most basic building block of it all.
The neuron. It's this beautifully simple processor of information, and it's the star of the show, both in biological systems, like, our brains, and in the artificial systems we're talking about today. So how does this little unit actually work? Let's break down how this tiny little information hub does its thing. First, you've got signals coming in through the dendrites. Think of those as the inputs. Then the cell body takes all those signals and processes them, basically deciding if there's enough of a jolt to do something. And if there is, boom, it fires. An electrical pulse shoots down the axon, that's the output, all the way to a connection point with other neurons, which we call the synapse. It's a simple, elegant little dance. Input, process, output. But here's the catch. A single neuron all by itself is frankly not very impressive. It can't really do much of anything on its own. The real power, the real magic, isn't in that single unit. It's in what happens when they all connect. Because when you take billions, and I mean billions, of these simple little units and wire them all together, the behavior that emerges from that network becomes incredibly, profoundly complex. The magic is in the connections. And if you need any proof of that, you don't have to look very far. I mean, the system that's processing my voice and making sense of these words right now, that's Exhibit A, your brain. It's where learning and memory and even consciousness happens.
Which naturally brings us to a huge question. If nature already built this absolutely incredible system, why are we going through all the trouble of trying to recreate it? Well, it turns out there are two really powerful reasons. On one hand, it's about pure science. Neuroscientists are building these models to try and unlock the secrets of our own minds, to understand cognition and find cures for awful diseases like Alzheimer's. And then, on the other hand, it's about engineering. AI researchers look at the brain and just say, wow, that is one heck of an information processor. Let's borrow some of those ideas to solve really hard problems that normal computers are terrible at. But this right here brings us to one of the most important things to remember from this entire explainer. Artificial neural networks, or ANNs, are inspired by the brain, but they are absolutely not copies of it, not even close.
And this quote just nails it perfectly. Think about it. We learn the principles of flight from watching birds, but we don't build a 747 with feathers and flapping wings, right? Of course not. We took the core concepts, lift, drag, thrust, and we engineered something totally different for a totally different purpose. It's the exact same idea here. ANNs ignore almost all of the messy biological details.
So then, what is it about this engineered, brain-inspired approach that makes it so different from, say, the computer you're watching this on right now? Well, the answer really comes down to two fundamental design choices. Okay, so this slide breaks down two game-changing differences. A traditional computer has one central brain, a CPU, that does things one at a time in a sequence. A neural network is the complete opposite. It's distributed. It's like having thousands of tiny little processors all working at the exact same time in parallel. The second huge difference is data. In your laptop, memory's over here and the processor's over there. In a neural network, they're woven together. The processing and the memory are integrated. The network is the memory. And that whole idea of parallel processing, it's absolutely critical. It is the very reason why GPUs, yeah, the graphics cards that were first designed to make your video games look pretty, have become the absolute workhorses of modern AI. They are just perfectly built to do tons of simple calculations all at once, which is exactly what a neural network needs.
Which leaves us with one final, pretty fascinating question. If these artificial neurons aren't made of actual biological cells, then what on earth are they made of? Well, we are going to uncover that answer next time. Thanks for joining me.